Hello, ladies and gentlemen. I am Boutheina Ghaddab. I received my PhD degree in chemistry from the Université de Franche-Comté in 2012. I am now research associate in the chemistry department of the Université de Québec at Montréal. My current research interests are 2D materials and their application for gas sensing. It is my pleasure to participate in the IEEE International Conference on Flexible and Printable Sensors and Systems. Today, I am presenting to you some results concerning my work entitled Flexible Gas Sensor based on MoSe2-Mo2C Heterostructure for Hydrogen Sulfide Detection at Room Temperature. This work was carried out in the open laboratory of Professor Mohamed Siaj. Gas sensors can detect the presence and the concentration of a specific gas in the atmosphere. They are very useful for environmental monitoring, industries, public safety, and medical diagnostics. Sensors are constructed from two main parts: a sensitive layer allowing the recognition of the gas with which it interacts, and a transducer system transforming the interaction into an electrical or optical signal. Among the chemical sensors, the most studied devices until today are the resistive sensors. This sensor can measure a variation of the electrical resistance as a function of time after exposure to the pollutant. The performance characteristic of this sensor is based on some properties including sensitivity, selectivity, stability, optimum working temperature, detection limit, and response and recovery time. During the last 3 decades, nanomaterials have been widely used in gas sensing devices. In particular, metal oxides are widely used because of their high sensitivity and fast response time. However, they usually work at high temperatures and they are not selective. Although conducting polymers-based gas sensors can work at room temperature, but they are sensitive to humidity and degrade quickly. Carbon nanotubes are also used as sensitive materials for gas sensing because it can work at room temperature. However, they have poor recovery that limit their application. For these reasons, recent studies have suggested alternative sensing materials for the development of efficient, sensitive, selective gas sensor operating at low temperature. Among the new sensing materials, the two-dimensional materials with novel and unique electronic, optical, and mechanical properties have attracted much attention because of the large absorbing capacity of gas molecules and strong surface activity. Various layered 2D materials have been studied so far for gas sensing applications. Other than graphene, the use of transition metal decalcogenide, including MoS2, WS2, MoSe2, and WSE2, as sensitive material for gas sensing applications, has attracted much attention. This progress was reflected in the increasing of the number of scientific articles published, particularly in the past few years. This interest to TMD material is due to their properties including large surface to volume ratio, high electrical conductivity, and like graphene, TMD have the potential to exist in more than one possible crystal structure: semiconducting 2H structure and semi-metal 1T structure, and the simplicity of doping and functionalization with the intention of improving their detection properties. In this research, the main objective is to study gas sensing properties for TMDS materials like MoSe2. In fact, its structure is similar to MoS2 and the electric mobility of 2D MoSe2 is higher than MoS2. To improve the performances of MoSe2 gas sensor by the modification of its surface by the synthesis of MoSe2-Mo2C hybrid material. The choice is based on recent studies on the absorption properties of transition metal carbides recorded, where they are used as gas sensing channels to improve gas sensing properties. The gas detected for this project is hydrogen sulfide. For an industrial application required low-cost flexible sensor able to detect 100 ppb of hydrogen sulfide at room temperature. So for the sensor elaboration part, MoSe2-Mo2C was synthesized by hydrothermal method using hydrazine as a reducing agent and molybdenum and selenium as starting materials. Then, the powder obtained was heated at 715 degrees Celsius with a mixture of argon, hydrogen, and methane at optimal conditions to obtain MoSe2-Mo2C. The characterization by Raman spectroscopy and high-resolution transmission electron microscopy confirming the formation of Mo2C on the surface of MoSe2. In fact, MoSe2-Mo2C form nanoscale heterostructure within the carbonized MoSe2. Finally, the sensitive material was obtained from dispersed MoSe2-Mo2C powder in the ethanol. The suspension was then stirred for 1 hour and sonicated during 1 hour. The thin film was deposited by drop casting on the flexible Boutheina tetraphthalate substrate, on which are deposited carbon electrodes, then dried at 60 degrees Celsius overnight. Here is the gas detection bank developed in the lab. The gas sensing properties of the sensor were tested in a Teflon chamber in the presence of hydrogen sulfide. The concentration of the inserted H2S gas was monitored using a Figaro standard gas sensor. To examine the gas sensing performance of the hybrid sensitive material, two sensors based on pristine MoSe2 and MoSe2-Mo2C were exposed alternately to 100 ppb of H2S and to air at ambient temperature. As shown here, the MoSe2-Mo2C enhanced the sensitivity to H2S compared to pristine MoSe2 by up to 6 times. It is noted that after gas injection, the resistance turned back to the original value when the sensor is exposed to air. The test of reproducibility on 3 sensors indicates that the sensor has good reproducibility and stability validated using of drop casting technique to produce reproducible sensors. This first experiment highlights the use of MoSe2-Mo2C as a sensitive material for the detection of low concentration of hydrogen sulfide at room temperature. Herein, the electrical response recorded at room temperature for MoSe2-Mo2C based sensor for different H2S concentrations. This sensor resistance is shown to increase when the concentration of H2S is increased with enhanced sensitivity. These results demonstrate that the sensor behaves as a p-type semiconductor material. The sensor shows high sensitivity to H2S since very low concentration. 100 ppb were detected at room temperature as compared to the literature for MoSe2-based H2S gas sensor when the operating temperature for this sensor is 200 degrees for the detection of the same concentration. The results obtained with MoSe2-Mo2C sensor at different concentration of H2S led to a linear behavior of the calibration curve between 100 ppb and 1 ppm. This confirms that our sensor can be used for the detection of very low amounts of H2S in R. Mechanical stability tests were performed to verify possible distortion of our flexible gas sensor that may occur during the resistance measurement, which in turn may lead to error of gas concentration measurements. So, like we see in this graph, the resistance of the sensor shows very negligible changes at different bending angle compared to the resistance change in the presence of the gas. Finally, MoSe2-Mo2C sensor was also exposed to humidity and different gases and volatile organic compounds like ammonia, benzene, ethanol, and acetone to check the sensor's cross selectivity at room temperature. The sensor performed the height response value to 100 ppb of H2S compared with the other tested gases at the concentration lower than 30 ppm of increasing gases. Moreover, MoSe2-Mo2C sensor has a poor selectivity in the presence of high humidity of high concentration of interfering gases. The basic principle of gas sensing in hybrid material is mainly based on the charge transfer processes between gas molecules and the surface of sensing materials. TMDS behave as N-type semiconductor intrinsically. The absorption of oxygen molecules from the environment can introduce the p-tip doping of MoSe2-Mo2C devices by increasing the Hall density. When exposed to H2S, reducing gas, the materials acts as a charge acceptor, which leads to an increase of negative charge, and the number of holes decreases, leads to the resistance increase. The reason of the significant improvement in gas sensing performance on hybrid material can be mainly attributed to the addition of Mo2C. It encourages the absorption of gas molecules on the surface of the material, thereby facilitating the charge transfer process and enhancing the response of the gas sensor. In conclusion, we have successfully developed a low-cost and flexible gas sensor operating at room temperature. The novelty of this study is the use of the MoSe2-Mo2C material as a sensitive layer for resistive gas sensor to detect 100 ppb of hydrogen sulfide at room temperature. Mo2C plays a significant role in the enhancement of the detection of the nanocomposite layer. We understand and propose a detection mechanism. The selectivity sensing to humidity and interfering gases remains a challenge for these devices. We can improve its selectivity by a surface functionalization with metal nanoparticles like platinum or gold. Finally, I would like to thank Professor Mohamed Siaj for the opportunity that he gives me to work in his laboratory. I would like to thank Tran for their part of synthesis and the characterization of the material. I would like to thank Professor Ricardo Izquierdo for his collaboration and Mohsen Kitabi for the electronic part of sensors. Thank you, and any questions?